Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln. And in this video, I want to have a look at one of the important parameters for helping understand how galaxies evolve, and that relates to the dark matter halos that surround them basically. That has a very big influence on how the galaxy at the center is going to evolve, and that's the dark matter spin parameter. And you've got the equation there. We're going to kind of explain what that is, explain why it's important for galaxy formation, and maybe how we can actually determine what the value of that spin parameter is as well. So just to recap on galaxies, so if you're not aware, galaxies are these enormous systems of stars, gas, dust and dark matter, and they're gravitationally bound. So some of them basically rotate like a disk, some of them are more spherical like your elliptical galaxies, but all of these are thought to have dark matter halos which are bigger than the galaxies themselves. So there's lots of different sorts of galaxies, different sizes, different shapes, depending on how old they are, the evolutionary phase, where they are to their environment, how they interact. So you've got a whole range of different sizes and shapes, but the dark matter still is very important for all of these. So from observations then, we do think that the vast majority of galaxies are surrounded by these dark matter halos. You've got the galaxy kind of in the center there. That's a spiral disk-like galaxy I've used as an example, but it's true for most galaxies. And then you have this fairly extended dark matter halo which goes well beyond the outer parts of the visible part of the actual galaxy that we can see. So this dark matter halo goes much further than the visible part, quite way further than that. Okay, so whilst it's not visible, we do think they're roughly spherical in shape, and that comes from other observations which we can use using gravity, essentially. So they do interact gravitationally, they don't interact in other ways really. We can't visually see dark matter, but we can see its gravitational influence on the galaxy and the environment around it. So we do think that these dark matter halos are roughly spherical, and that's not necessarily true. I've done a separate video on dark matter shape parameter, and you do get ones that are kind of a bit more elongated, but let's just say they're roughly spherical for the purpose of this video anyway. So if we then kind of zoom out a little bit into galaxy clusters, this is where we have multiple galaxies kind of in an overdense region of the universe, and they would be a cluster or even a group. Actually, a group's a bit smaller than a cluster, and they also then have dark matter halos as well. So a galaxy cluster would have its own dark matter halo. You then may have like sub dark matter halos on different scales as well. So these are quite large structures, and again, we do know they're there, or infer that they're there, due to their gravitational influence on the environment and the galaxies that they are in and around. So this is a good example actually. So here you've got gravitational lensing. Now what happens here is you've got a background galaxy behind or at the back of the cluster, and that's being distorted gravitationally by the mass in the cluster, and the mass that we measure and the mass we can see in the galaxies don't line up. So we can actually calculate the kind of missing mass or the dark matter there from the distortion. And it works a bit like an optical lens. The rays of light, or the pathway of the light from the galaxy behind, is kind of bent around gravitationally. So they work in the same way. But anyway, this is how we kind of assume that we have these dark matter halos or dark matter in these big galaxy clusters. I'll come back to observations of individual galaxies at the very end. So the galaxy evolution, which is something that's very important for us to understand as astronomers, is dependent on the halo evolution. So whatever happens to the dark matter halo, it's going to imprint a signature onto the galaxy. That's going to affect how that evolves as well. And the dark matter spin parameter is going to be an important aspect of that as well. It's going to impact how that galaxy might start out and form and then evolve through its lifetime as well. So dark matter halos, they are pressure supported, but they do have this non-negligible angular momentum. So they're not fully rotating like a disk-like galaxy, like a spiral galaxy, for example. And what do we mean by pressure supported? Well, it just means that, let's say we have individual dark matter particles in this dark matter halo. They are moving more randomly rather than rotation wise. So this gravity, because if you just have gravity and nothing else, it's going to likely collapse. So it has to be balanced by something else, and it's balanced by the random motions of the dark matter as opposed to it being rotation supported. So something like, you've got a spiral galaxy rotating in a common plane, that might be rotation supported as opposed to pressure supported. And that's how we assume the dark matter halos to be. But they do have some angular momentum, so there is some kind of net rotation there, and that's what this dark matter spin parameter is concerned with, really. So where does it come from? Well, initially when these dark matter halos and then the subsequent galaxies are forming in the early part of the universe, there will be overdense regions and underdense regions, and neighbouring overdense regions can actually impart tidal torques onto other dark matter halos, essentially, and that can then give them some net rotation. So you've got these overdense regions in the universe, and the way they interact gravitationally can actually impart some angular momentum at the start. Now, obviously, depending on how they're interacting during that formation process, is going to dictate just how much tidal torque there is and how much angular momentum those dark matter halos subsequently end up with. So then, back to the spin parameter. The spin parameter is then going to measure the halo's angular momentum relative to its mass and its energy. So some are going to have high spin parameters, some are going to have low, and again it's going to be quite important for understanding the galaxy at the centre of that, how that evolves and forms and goes about its lifetime, really. So if we have a larger spin parameter, it's going to be more rotationally supported, and that's going to influence the disk formation. So if that dark matter halo is spinning faster, we can look at that and think, well, it's more rotationally supported as opposed to pressure supported, because you've got more rotation there. And as that disk forms at the centre or galaxy, that's going to influence that kind of in a non-negligible way, basically. So the spin parameter is given by this equation here. It's a dimensionless parameter, so it doesn't have any units or anything like that. You're just going to kind of get a number. And it's used to quantify the rotational support of these halos. So what are all those individual components there? Well, our J there is our total angular momentum of the dark matter halo. We've then got the total energy of the dark matter halo, and then we've also got the mass of the halo as well. And obviously you've got your G there, which is your gravitational constant. So if you can actually determine what the mass, angular momentum and total energy is of your dark matter halo, you can calculate its spin parameter. Now, on the lower end, a non-rotating system or a non-rotating dark matter halo is going to have a spin parameter of 0. So it's going to be more pressure supported. The motions of the individual components are going to be more random, and we basically have a 0 spin parameter if it's non-rotating. On the more extreme side, if we have a fully rotation supported kind of razor thin self-gravitating disk, then it's going to be just under a half. Well, it's about 0.4255, approximately, somewhere like that. And that means that it's kind of more rotation supported as opposed to pressure supported. So again, we don't have any units there. We have these values where we have an upper limit and a lower limit, just to kind of give you an idea of the range there, really. Now, how do we determine the spin parameter? Well, from observations, estimating it's pretty tricky. But what we can do is we can infer indirectly by looking at the galaxy. We can't see the dark matter halo, but if we look at the disk size and the rotation curve, we can infer things like the mass and other parameters of the dark matter halo as well. So if you're not familiar, I've got a rotation curve here of a spiral galaxy. You've got velocity on the y-axis and distance from the center, which would be your r. And we expect the further away you are from the center, that it would drop off and rotate slower but that's not what happens. They actually have a fairly flat rotation curve, and the only way to replicate that is by having additional mass in the outer parts and extending into this halo. So that's why we think they have dark matter halos. But anyway, you can observationally infer it indirectly from things like that, but it can be pretty tricky. But you can also directly measure it from simulations. So if you create a simulation of dark matter halos, this is kind of from the Millennium simulation where they modeled pretty much the entire universe, you can directly measure that because you know what the mass is and you know all the other parameters. So it's much easier in simulations, but it's also determined on how you set that up as well. So thank you for watching this video. If you enjoy the video or find them helpful, then do consider becoming a member of the channel. There's extra videos in the member section, but also it helps support the channel as well. So thank you for watching.